Hello everyone. Today we will deepen our understanding on Ampere's Maxwell law and we will extend it from integral to differential form. You recall that Ampere's law in its integral form is written as the closed integral of b dot dl, which is equal to mu naught times the enclosed current. So where B is the magnetic field, C is a closed loop, also called the Amperian loop, mu naught is the permeability of free space, and I anc is the net enclosed current by the loop. This law works beautifully for steady currents. For instance, in a long straight wire, Ampere's law lets us calculate the magnetic field as B equals to mu naught I over 2 pi r. However, in the mid-19th century, Maxwell realized that Ampere's law, as it stood, had a major inconsistency when applied to time-varying electric fields. So what's the problem? Or what was the problem? Well, imagine a capacitor being charged. During charging, the electric field between the plates changes over time. The current flows into the capacitor plates but does not cross the gap between them. If we apply Ampere's law to an Amperian loop surrounding one plate, we find that the enclosed current is not zero. So there is a magnetic field, but if we draw the loop in the gap between the plates, the enclosed current is zero, suggesting no magnetic field. So here we have chosen the same Amperian loop in situation 1 and situation 2, the same Amperian loop, but the surface that is enclosed by this loop is different. We are free to choose the surface that is enclosed by the Amperian loop, but in one case the current penetrates one of the surfaces, and in the other case there is no current penetrating the second surface. So this brings us to some sort of contradiction that Maxwell solved elegantly. This contradiction arises because the original Ampere's law does not account for time-varying electric fields. So what did Maxwell introduce? Well, Maxwell introduced the concept of displacement current to resolve this inconsistency. He proposed that a change in electric field contributes to the magnetic field, just like a conventional current does. This displacement current, I sub d, is given by epsilon naught, the derivative of the electric flux with respect to time, where epsilon naught is the permittivity of free space, and the electric flux through a surface is the integral of E dot dA. Maxwell then modified Ampere's law to include both conduction current and displacement current. Now, if you are in situation 1, the conduction current penetrates the surface that you've chosen, and if you are in situation 2, there is no conduction current, but there is this displacement current that penetrates the surface that you choose. So in this case, no matter what surface you are going to choose for your Amperian loop, you will get the same result. So the closed integral of b dot dl is equal to mu naught parenthesis I enclosed plus epsilon naught d phi sub e over dE. This is the Ampere-Maxwell law in integral form. It unifies the effects of moving charges and changing electric fields on magnetic fields. So the magnetic field is created by an electric current and by a varying electric flux. Now, let's move to the differential form of Ampere-Maxwell's law. First, let's have a look at Stokes' theorem. So to rewrite the integral form as a local expression, we use the Stokes' theorem, which relates the line integral around a closed curve to a surface integral of the curl of a vector field. So in mathematical forms, this is the closed integral of b dot dl across a curve is equal to the integral on the surface of the rotation of b dot dA. Substituting this into the Ampere-Maxwell law, we get that the integral of the rotational of B dot dl is mu naught times the integral of J dot dA plus mu naught epsilon naught the integral of partial of E with respect to T dA. Here I have written the enclosed current as the integral of the current density, so that I have now integrals everywhere. And look that all these integrals are along a surface, which is not a closed surface, but is a surface enclosed by a closed loop. Since this equation must hold for any surface, the integrands must be equal. So the rotational of B, the curl of B, is equal to mu naught J plus mu naught epsilon naught partial of E with respect to T. This is the differential form of the Ampere-Maxwell law, also known as Maxwell's fourth law. It states that a current density J produces a curl in the magnetic field B. A time-varying electric field, delta E delta T, also produces a curl in B. The differential form of Ampere-Maxwell law is local. It tells us that how the magnetic field behaves at every point in space. So the magnetic fields from currents, the term mu naught J is the familiar contribution of current density to the magnetic field, consistent with Ampere's law. The new term mu naught epsilon naught partial of E over delta T shows that time-varying electric fields generate magnetic fields, even in regions without conduction current. So that also works in a vacuum. This correction completes the symmetry in Maxwell's equations, as changing the magnetic field, partial of B with respect to T, induces an electric field as described by Faraday's law, so that the curl of E is minus partial of B with respect to T. The Ampere-Maxwell law combined with Faraday's law leads to the prediction of electromagnetic waves. We will see that soon. A time-varying electric field generates a magnetic field, which in turn generates an electric field, allowing waves to propagate through space. This underpins all of electromagnetism and forms the basis of technologies like radio, microwaves, and optics. The displacement current ensures that the law of conservation of charge is upheld. Without it, Ampere's law would fail for time-varying fields. So, Ampere's law originally accounted for only the steady current. Maxwell introduced the concept of displacement current to account for changing electric fields, leading to what we can call Ampere's Maxwell law. The integral form is a closed integral of B dot dl is equal to mu naught I enclosed plus epsilon naught, the derivative of the electric flux with respect to time, which used in Stokes' theorem becomes the differential form curl of B is mu naught J plus mu naught epsilon naught partial of E with respect to T. This law plays a pivotal role in the unification of electric and magnetic phenomena and in the propagation of electromagnetic waves. Let me know the questions in the comments below, and may science be with you.